In this video, we're going to talk about how the Sami people turned frozen ground and crooked branches into a structure that could outlast an Arctic winter. Most people think turf houses were just primitive holes dug into the ground, or something from Minecraft, crude shelters for people who had no other choice. But the reality is far more extraordinary.
These structures were advanced thermodynamic machines, engineered without blueprints, metal tools, or modern materials, yet capable of holding 60 to 70 degrees Fahrenheit inside while the Arctic raged at negative 44 degrees Fahrenheit outside. The frame, the layers, the fire placement, the very shape of the walls, every single element was a calculated solution to a problem that would defeat most modern engineers.
And the most insane part? The worse the blizzard got, the stronger the structure became. By the end of this video, you'll have a completely different understanding of what a house can actually be.
In the Sapmi region, the sky has no memory of daylight. Fine snow is hurled at hurricane speed, tearing against exposed skin like thousands of burning needles.
The temperature plunges to negative 44 degrees Fahrenheit. In this lethal cold, conventional architecture fails utterly. Rigid walls crack, iron joints shatter, and carefully engineered rooftops buckle under the weight of accumulating ice. The question is never simply how to build a shelter. It is how to engineer survival when the only materials available are crooked birch branches and blocks of frozen earth as dense and unyielding as stone.
The Sami answered that challenge with the Goahti. It is not a hut, it is a sophisticated elliptic paraboloid structure, a thermal machine designed to vanish into the landscape, drawing its strength from the very forces that seek to destroy it.
The hunt for the right wood. Every Goahti begins with a silent search through the low, wind-twisted birch forests of the Arctic. Here, straight timber is essentially non-existent, and to a Sami builder, that is no problem at all. Where Western engineering traditions worship right angles and uniform lumber, the Sami recognized that nature's imperfections were an untapped reservoir of structural genius. The heart of the Goahti skeleton, called the bilgi or belg frame, demands exactly 4 birch trunks with matching natural curves. These are not ordinary trees. They are organisms that spent decades bending themselves against prevailing winds, fossilizing tension and resilience deep within their dense wood grain. Rather than forcing timber to curve through heat or machinery, a process that overstretches outer fibers and compresses inner ones, seeding latent fracture points, the Sami simply borrowed curves that nature had already perfected. The structural strength was not manufactured, it was inherited.
The skeleton, an elliptic paraboloid. When 2 pairs of these pre-curved poles are raised and lashed together at the apex with a load-bearing crossbeam, something remarkable emerges: the elliptic paraboloid. Modern engineers required complex mathematics to decode what Sami craftsmen had mastered through generations of observation. In a conventional house, vertical walls support a roof by creating rigid joints, and those joints are exactly where catastrophic failure begins. The Goahti eliminates that vulnerability entirely. Imagine 10 tons of dense, wet snow pressing down onto the dome. In a standard structure, that weight would seek out flat surfaces and rigid connections to exploit. In a Goahti, the elliptic curve of the bilgi frame acts as a smooth conduit for force. The compression travels from the apex downward along the curved poles, distributing evenly across the rocky ground below, no single point ever bearing more than its share.
Here lies one of Arctic architecture's great paradoxes. The heavier the snowfall, the more the structure's poles are gripped to the earth. Snow does not threaten the Goahti. It reinforces it, transforming a lightweight wooden skeleton into something close to impregnable. Equally critical is what the frame deliberately lacks. There are no iron nails, no rigid wooden dowels, no drill holes weakening the grain. Metal is a liability in extreme cold. It conducts heat poorly, contracts violently at negative 44 degrees Fahrenheit, and becomes as brittle as glass under wind load. An iron nail in Arctic conditions is nothing more than a crack waiting to propagate. Instead, the Sami relied on the wood-on-wood principle. Rafters rested against the main frame and secured with flexible bindings of animal sinew or tightly braided bark.
This gives a structure a quality called dynamic stability. When a gale sweeps through, the Goahti does not brace against the blow, it breathes with it. The bindings expand and contract, absorbing the storm's energy rather than snapping under it. The result is a frame weighing only a few hundred pounds, yet capable of supporting an entire hillside's worth of compacted turf above it.
The shell. Layers built for survival. Once the bilgy skeleton stands, the process of enclosing it begins, and every layer serves a precise function in a carefully ordered system. The first coat pressed directly against the wood is birch bark, layered in overlapping scales that mimic the structure of deep-sea creatures. This choice reflects a sophisticated grasp of material science. Birch bark contains natural oil resins that render it waterproof and resistant to decay for centuries, even when buried in soil. This scaling directs rain and snowmelt away from the wooden frame below, preserving the bilgy's elasticity and preventing fungal intrusion. Crucially, birch bark is a one-way barrier. It repels liquid water while still allowing the structure to breathe, preventing moisture from accumulating inside.
Atop the bark comes the defining feature of the Goahti, massive slabs of tundra sod, cut thick with their root networks intact, piled onto the structure until the walls reach 3 to 5 feet of depth at the base. This earthen layer is not merely insulation, it is a thermal battery. Throughout the day, it silently absorbs heat radiating from the central hearth, storing energy deep within its compressed root matrix. When outside temperatures plunge to lethal levels overnight, the sod begins releasing that stored warmth slowly and steadily, completely eliminating the thermal bridges, those dangerous heat escape gaps, so common in modern construction. In a Goahti, heat has nowhere to go. It is held captive within a solid mass of earth and roots.
The sheer weight of this sod layer, which might seem to threaten the structure, is in fact what anchors it. The mass pins the bilgy skeleton permanently against the rocky ground, and the interplay between the Earth's weight and the wood's flexibility creates a dynamically stable system that can endure storms capable of obliterating modern prefabricated buildings. When snow finally falls and blankets the mound, it doesn't threaten collapse. It serves as the final insulating layer, completing a shell that nature itself helps construct.
The hearth, engine of a thermodynamic system. The soul of the Goahti is the Iran, the central fire pit, placed at the precise geometric center of the floor. Its position is deliberate, not ceremonial. Radiant heat from the Iran spreads uniformly in every direction, striking the curved inner walls and deflecting back into the living space rather than escaping upward. The entrance is engineered as a long, low, narrow corridor, a cold trap. Outside air, being denser than warm air, flows low to the ground. This corridor intercepts the cold before it can flood the interior, funneling it toward the Iran where it is drawn in, heated, and sent upward. Unlike conical tent designs where hot air escapes through the peak almost immediately, the elliptic dome here performs differently.
The heated air clings to the curved ceiling and curls back down along the walls, wrapping the sleeping and living areas in a continuous thermal envelope. Smoke and exhaust are guided out through the roof, opening at the apex, creating a natural chimney effect that keeps interior air oxygen-rich without hemorrhaging warmth. The narrow interior dimensions are not an accident of tradition, they are deliberate engineering. A smaller air volume requires less energy to heat. Every person gathered inside radiates roughly 100 watts of body heat per hour.
When the whole family assembles, along with their sled dogs, that collective thermal output merges with the Iran's flame and the insulated earthen walls to sustain an interior temperature of 60 to 70 degrees Fahrenheit, while the world outside hovers at negative 44 degrees Fahrenheit. Sleeping platforms raised roughly 1 foot above the floor complete the system. Layered with fresh birch branches and thick reindeer fur, both exceptional at trapping still air, these platforms position the body in the upper warm zone, completely isolated from the cold air layer that pools at ground level.
Smoke as a resource. Inside the Goahti, even combustion byproducts are put to work. The Sami never regarded hearth smoke as a nuisance to be eliminated. Instead, they suspended strips of reindeer meat and freshly caught fish on wooden racks positioned directly in the smoke's path as it drifted upward through the birchwood rafters toward the roof opening. Birchwood smoke carries phenolic compounds and organic acids that penetrate deep into meat fibers, forming a chemical barrier against mold and bacterial growth. What in other cultures is an engineering headache? Managing ventilation in a sealed insulated structure, the Sami converted into a superior food preservation system. By the time smoke exits through the apex, it has fulfilled multiple missions: warming the living space, drying the food supply, and reinforcing the energy reserves that make survival through the months of perpetual Arctic darkness possible.
Clothing as architecture. The Goahti's thermal logic does not end at the walls. Reindeer skin clothing functions as a portable extension of the structure itself. Each hair of reindeer fur is hollow, trapping microscopic pockets of still air against the skin, a natural insulation mechanism that no synthetic material of the era could rival. When a person sits near the Iran, their clothing works in concert with the elliptic dome, forming a double cocoon. The heated air of the interior and the fur's trapped air layer together ensure warmth is held close to the body. When they step outside to face the blizzard, that same garment becomes their only shield, a mobile wall, carrying the logic of the Goahti with them.
The philosophy of vanishing. Perhaps the most profound dimension of the Goahti is its intended impermanence. This structure was never designed to outlast its purpose. Built to follow the biological migration rhythms of the reindeer herds, the Goahti was meant to be abandoned when the pastures were exhausted and reclaimed when the community returned.
When the Sami departed, they left no permanent wound on the landscape. The sod layer quietly merged back into the tundra. Grasses grew over the old dome, erasing the human trace beneath a shroud of moss and forest. And yet, when a family returned decades later, they would often find the curved birch timbers still lying in the earth, intact, neither rotted nor broken, preserved by the protective oils of the birch bark that once covered them.
The Goahti endures not by defying time, but by cooperating with it. It stands when needed, dissolves when not, and waits patiently for life to return. A mound of earth, green in summer, white under winter, sheltering a fire that burns through generations. That is the legacy of Arctic survival engineering, not conquest over nature, but a conversation with it so fluent that the line between the two disappears entirely.